All right, welcome everybody to the second and final Dubai lecture for 2023-2024. Again, our speaker today is Professor Teresa Head-Gordon from the University of California, Berkeley. Today she's going to tell us about a slightly different topic than yesterday, right? Today she's going to tell us about physics-inspired machine learning and give us a status report on the sort of predictability in terms of chemistry of these methods. Although I gave a background, or Teresa's background yesterday, I'll just give a brief summary today. Teresa at the moment is the Chancellor's Professor of Chemistry, Bioengineering, and Chemical and Biomolecular Engineering at the University of California, Berkeley. She is also a Senior Faculty Scientist in the Chemical Sciences Division at Lawrence Berkeley National Labs. Teresa was born in Akron, Ohio, and received her earned a bachelor's degree in chemistry at Case Western, and that was followed by a PhD in chemistry with Charlie Brooks at Carnegie Mellon. From there, she went over to work with Frank Sillinger at the Bell Labs on water and protein folding. And after that, she joined the Lawrence Berkeley National Labs as staff scientist, and then quickly moved through the ranks of assistant associate and a full professor at Berkeley. I want to just mention again, Teresa research group has quite a breadth of topics that they cover. I think you'll be duly impressed. But the main focus is development of new computational and theoretical techniques for describing condensed phase systems. Again, ranging from macromolecular assemblies to interfaces and biocatalysts and molecular liquids, et cetera, et cetera. And today, she's going to tell us a little bit more about machine learning, which is very popular. And let us know how it goes. Let us know how it goes, right? Yeah.
Give you the status report. Okay.
And thank you again for the great lecture yesterday, and thanks again for coming and giving too, right? Especially this week, right between the APS and ACS meetings.
I know. I planned it that way. So, anyways, but I've had a really enjoyable visit. So thank you everybody for, and also the students for hosting me, who ran me around and broke up your day for me. So I appreciate that, and also for coming out to dinner with me, because I know that that's family time and greatly appreciated. So yeah. So yesterday I talked mostly about physical models and ideas. But there's this new kid on the block. It's not that new, actually. Machine learning has been around for a while, and it goes through periods of where it becomes popular, and then it goes kind of, dormant for a while. And so when I was at Bell Labs, I actually worked with Frank. Frank and I worked a little bit on machine learning, and early neural network kind of stuff ideas. And it died out. It sort of died out then soon thereafter. And then for some reason, it's, I think, here to stay. And of course, the students won't appreciate the fact that when we were growing up during this time, that we were living through the golden age of computing, right? So, around the time that I was born, Gordon Moore was sort of, who is the co-founder of Intel, was noting this transistor density was actually increasing roughly every 18 months. And you can sort of equate that as equivalent to compute power. And so here, you can sort of kind of resolve the transistor density here, but by the time we get just, 20 years later, you can no longer see these kinds of features. And we know that that led to sort of a huge revolution in the kinds of things that can be done. And so we're over, Moore's law kind of has petered out. We're looking at new computing paradigms. But what we are in now is the so-called golden age of data. Now, there's this dubious quote here. As far as I've tried to find this quote, and I can't find it, so don't rely on it, okay? But the supposition is that the amount of data that's been created, 90% of it sort of occurred in between 2016 and 2018. Okay, but maybe another kind of fun way of looking at it is that when you think about these prefixes, we're in the Zeta prefix regime in regards to digital data, and that we've got Yoda, and then otherwise we're going to have to start, thinking about new prefixes. So the idea here is that these are starting to become combined, and what I'm, I think more convinced is that this time it's here to stay. Okay, so now let's start grappling with it. And so I wanted to kind of give this example of chemical reactivity It's what we care about, chemical transformations. And, you know, when you have a physical model with all of its limitations, it's physics, you know, it's like you know something and that you can lean on it. You can say, you know, I want to study a nanocage. I want to understand chemical reactivity. So there's sort of certain levels of theory and kind of things that go on. I'll come back to this in a second. And then, you know, here's some enzymes and how do we go about designing them? And then the fact that, you know, how do you drive chemistry under alternative environments like micro, you know, under kind of confinement or at interfaces, which is the thing that I spoke about yesterday. And I wanted to kind of just go through quickly an example of this chemical reactivity in nanocages. So my colleagues at Berkeley, Ken Raymond had developed this inorganic chemistry to create self-assembled nanocages. And these nanocages have metal vertices and they have these ligands that self-assemble into these little cages. And then Dean Tost, who's one of my colleagues too, was then wanting to see if you could sort of accelerate reactions in them. And so Dean's done a number of these where off of this gold complex, one can perform carbon-carbon reductive elimination, okay, in these. And it fits Michaelis-Menten kinetics, so it acts like an enzyme. You get about I think about 8 orders of magnitude compared to the uncatalyzed reaction. So the question is why? Like, why do these work so well? And so what we have typically done, and this is work that was done by Valerie, who's now an assistant professor at Virginia Tech, and Wan Lu, who's now assistant professor at UC San Diego, is that we wanted to develop a theoretical understanding of that. And first thing we want to do is define the transition state. You know, what is it about this environment that gives rise to a lowering of the free energy of the transition state? But really what I wanted to kind of, well, what I'll come back to is just sort of cut to the chase is that it turns out that it encapsulates a couple of water molecules, and those water molecules give rise to my favorite descriptor, electric fields, that when projected upon these carbon gold bonds, help it break, and therefore how to then reestablish new carbon-carbon bonds. But the thing that I wanted to say, in order to get to that conclusion, we had to develop this whole physical model where we're trying to work developing the free energy surface in a collective variable space where we hope is, you know, realistic. And so this is a technique called metadynamics. You find these lower manifold and you run dynamics in them in order to be able to characterize the free energy that you can trap the transition state. And then if your transition state is actually a real transition state in the full dimensional space, you start at that transition state and you do committer analysis and you say, okay, 50% of the time I end up in the reactant and 50% in the product. And so you got it right. And, you know, we get a transition state lowering within the nanocage that's, in pretty about an order of magnitude better than the actual experiment. But I think that that's sort of pretty good. And the thing that I want to kind of emphasize is, you know, this is months of ab initio workflows, you know, but the thing that I want to emphasize is the fact that, you know, that it's predictive and it's ready for discovery, which is that the next time I want to try to discover some other kind of chemical reaction, I can go back to these same techniques because we have a physical model, we're on a physical potential energy surface, and it should be predictive, okay? Now, can the machine learning do better? That's my question. That's the thing that I've been interested in. And so I think the general problem with machine learning is that of course we got to rely on data, and data generation of any kind of quality is going to be expensive. And furthermore, I'm going to argue, and my worry is that it will always be incomplete. And if it's incomplete, it's going to fail at some point. And in particular, it's going to fail whenever you try to predict something out of distribution, right? So out of distribution cases. All right, well, maybe we can recover from this. And so if I essentially came up with some good, what we call feature engineering, there's something about, you know, the physics that I can boil out of those physical models and essentially use those to signal to the machine learning that this is the things that are important. or the information that I get from a cheap calculation that makes the data generation affordable. Or, as I'll mostly focus on today, is that I just think that the way to go here is through hybrid machine learned physics models. Okay, so, all right. So I'm going to go through 3 examples today. I'm going to talk about machine learning that we've been doing for spectroscopic properties, and this is the prediction of, let's say, NMR chemical shifts. Okay, so let's talk about that. And here's some of the, this is the work we've been doing over time. Actually, this one with Paul Avasadas was a sort of a different topic, but it's a different, really shouldn't even be here. But the other ones are really dealing with the NMR chemical shift. This guy's at Facebook right now. This guy's at another machine learning company. This guy has started his own startup in machine learning. So the point is that that's where it leads you, is to essentially those kinds of jobs. Zhao Shu is in Martin's group, who we collaborated with, is also looking for industry positions. And so the point is that it's an area of growth. All right, but it's also a hard problem. Okay, that's a hard theory problem to get chemical shifts right. Okay, from ab initio. All right. The other example that I want to talk about is chemical reactivity. So I've already kind of outlined it here. And so therefore, it's really trying to learn the potential energy surface. And that's what I want to also talk about today as my second example of, how well can we learn the potential energy surface? And so we'll talk a little bit more about that. And so this is Mushtaba, who's at Pfizer doing machine learning. And there's Nancy, who just got a job at Schrodinger doing machine learning. And then this is a student in the lab right now, where we're using machine learning to do transition state optimization by learning Hessians, or by predicting Hessians, I should say. And then I'll give this final example. Ufan Zhang, was an undergraduate student here who was actually doing her research with Nandini. And she's now a graduate student in my lab. She's fabulous, okay? So she is fantastic. And so we've been developing some ideas about machine learning, about how it could be applied to these proteins, this class of proteins called proteins that have intrinsic disorder. And those are, I think the next frontier in structural biology is to be able to understand their function, which you often do through trying to understand their structure. But in this case, it's not a folded protein, it's an ensemble. And so therefore being able to predict the ensemble is another hard problem to do, because all of the experimental techniques are extremely underdetermined. All right, so let's begin with this chemical shift example. And why do we care about it? If we can actually measure it, okay, if you can measure it, then it's a very sensitive probe to the local electronic structure environment. And so let's take something like NMR crystallography. Well, what you can do is you can, take that chemical shift and build structural models. And from those structural models, be able to characterize small molecule chemistry, for example, pharmaceuticals, okay? Now, what's so great about chemical shifts compared to let's just simply doing X-ray crystallography is that it's extremely sensitive to hydrogen. And that's essentially what part of the molecule that you would like to know more about. All right, and so the thing is that, even hybrid function, you have to at least have hybrid functional DFT, okay, in order to make chemical shift predictions. Anything lower are going to be highly inaccurate. And these have heavy computational cost, even though Rob is essentially trying to beat that problem down. And so, but the idea here is that this is what I mean by expensive data generation. All right, and can machine learning do better? All right, so this idea that, okay, so the ab initio DFT methods are kind of scaling cubically with the number of, effectively atom size or beta set size. But the idea being is that that's the scaling law. And what we decided to do is we were going to say that let's assume that the feature that matters is the electron density. And then what I'm going to do is I'm going to create channels, okay, that are at different resolutions of the electron density. Okay, so that means that what you can do then is you can turn to a certain type of deep learning architecture called convolutional neural networks. Okay, so what are they good at? They're good at sort of, let's say, image classification. And And so why not just, instead of, showing it cute pictures of cats and dogs and all that kind of stuff, let's show them pictures of electron density. Instead of having red, green, blue channels, let's have essentially resolution channels of the electron density. All right, so this is what our method is. This is called this is a convolutional neural network, and it's a cartoon because of essentially the operations that are embedded in this actually are rather simple. So in other words, this is not a kind of an empty cartoon. These blocks essentially have really well-defined mathematical operations so that you could literally code this up based off of this sort of this type of representation. And then we were also doing something called dense nets. And really what it was is utilizing what are called skip connections, because skip connections in the architecture, so if you think about it, you're doing feed forward, and then to do error correction, okay, to get better agreement with the data, you've got to take derivatives that have to go all the way back to the beginning. And that is called gradient decay, okay, unless you have an architecture that does a skip to be able to allow that gradient to flow backward better. Okay, so that's something called dense nets, but there are variations on that. So that's what we did in 2019. And but the thing is that it needs data. It's a pretty deep architecture. We have expensive ab initio data, and the question is, how accurate can we get? All right, so the first thing you might think is we need data, okay, to be able to exploit an architecture like that. And that's why others had turned to less data hungry methods like kernel ridge regression, because those are meant for sort of small data type problems, okay? So they scale, however, as n cubed, okay? So therefore, if the data gets too big, they start becoming unwieldy. But the other thing that's good about them is that symmetry operations are baked in. And so what do I mean by that? But that means that if I predict a chemical shift and I present the network with a molecule like this, and I just do a trivial rotation, I should get the same chemical shift. But if you don't build that into the network, you will not get that. It will essentially give you a different chemical shift prediction. So there are these symmetry operations that get baked into it, like let's say a Baylor-Paranello network, which are, the fact that the network has to learn that certain properties like energies or chemical shifts are invariant. The quantity is the same under translations and rotations. All right, so when we start off with this finite amount of data, we can see that our original 3D dense model, okay, it doesn't perform as well until you get out to large data, because the CNN, the deep network, has capacity. And until you essentially can exploit that capacity, you can then only barely beat the KRR model. All right, but what we can do is called data augmentation, which is that why not just teach the network, okay, listen, here's the chemical shift. I just keep rotating the data and just give it different, rotations, let's say 8-fold rotations, and it's the same chemical shift. It's more data. And at the same time, it's more capacity that it can take on, but it's also teaching it, okay, about the fact that the symmetry of what the symmetry operation has to be. And so when we do when we actually train now with data augmentation, we now sort of comfortably start beating the original KRR method. And then you can do something called ensembles, which is that you do multiple machine learning models, pick, kind of do a jury vote and pick the best one, and that's then gives you a little bit more performance, okay? All right, so we can do this, but this idea that we would have to have data augmentation. Okay, so the second thing though that bothers me, as I said, about machine learning right now, is that how does it predict out of distribution? Okay, so for example, if we actually looked at the performance of this, we do great on hydrogens because all of the data of any organic molecule, half of it's hydrogen, right? And so the point is you got a lot of hydrogen data. We perform, better, but not as good as the hydrogen data for carbon or nitrogen or oxygen. And so you need data. So you just need more data. And furthermore, it's telling you that you can't really predict out a distribution because you haven't seen enough examples. All right. So what we then did is turn to this idea of saying, okay, well, let's try to inform a physics infusion into the machine learning model. And so this was work that was done jointly with Martin's group. Now, Martin's group had actually come up with some composite methods that allowed them to argue that the composite methods that they were using were equivalent to CCSD parenthesis T in the complete basis set limit. Okay, so therefore you got this high quality data. And so this would be almost impossible. The composite method, well, we can do some. We can get away with, we can do more. All right, but the idea was to then say, why don't we try to infuse it with the magnetic shielding, the diamagnetic and the paramagnetic components into it. So therefore, what we're going to do is we're going to take the DFT calculation in order to get the labeled data, but then we're going to extract this physics-based information, and then we're going to use it in combination with our just in this case, just a multi-layer perceptron network, nothing fancy, okay, that will then be combined, okay, to another network that will make a chemical shift prediction. So this is what I mean by here's the physics side, here's the machine learning side, you combine them and you essentially now try to make a prediction. But you're trying to infuse it with some information, so you hope that you're going to be able to make arbitrary chemical shift prediction. Even if you haven't seen that kind of chemistry before. All right, so what we did was another thing, which is that we also developed what we think is a novel active learning procedure, which is let's train a network. So there's this famous Annie data set. This Annie data set was created by Adrian Breutberg and Ola Isayev, who's at Carnegie Mellon. And they have like 20 million data points of energies, okay, at not a very good level of DFT, but nonetheless, they have about 57,000 molecules in different configurations, therefore resulting in 20 million configurations of organic molecules up through 8 heavy atoms. So what we decided to do was to say, well, let's learn chemical shifts, let's calculate those chemical shifts on up to 4 heavy atom data. So we train, okay, but we train now multiple models. We train like 4 independent, okay, machine learned models, okay. So now what we do is that we then try to predict on 5 heavy atom data, and the 4 models will essentially either say, hey, we all can predict that. We all kind of learned that chemistry for the 5 heavy atom. But the ones that are excited too new, there'll be a huge variance among those models. And therefore, we're going to then harvest that data of the 5 heavy atom data that will now retrain the model to essentially account for new types of data. And therefore that keeps data, requirements low, excuse me. That keeps data requirements low, but it also is essentially telling you that you're learning something, okay? Because some of the 5 heavy atom data was well understood, and then you keep bootstrapping. So then you train this 5 network, 4 model, machine learning model, try to predict it on 6, look for the variance, et cetera, et cetera. Okay, so you build up the data that way, and we can see that the RMSE is going down, okay, for chemical shift predictions as we move across that data. All right, now, then we wanted to apply it. And so this is right here, these are these, what are they called? Sorry, these are the vanusols are these certain kinds of drug molecules that are very rigid. They're also sort of typically the data is taken in organic solvents, okay? So they're natural products, that's what they are. And so the main point here is then, can we predict a natural product? You know, these are much bigger than our 8 heavy atom system. Like we got, you know, 30 some, 40, 50 atoms. And what I'm showing here is that, you know, compared to a DFT calculation, you know, that we can do a lot better than that. And so then in the low level, if we just simply took the low level data, but then if we do delta learning to learn the composite method that was developed in Martin's group, then we're down here. And so we do get sort of overall improvement in chemical shift prediction that's extensible, okay, to new molecules, much bigger molecules, okay. All right, so that's an idea of essentially trying to get machine learning to be predictive, okay, and therefore there's sort of, you know, and how to get it to sort of understand chemistry as opposed to just trying to fit chemistry, okay, by just essentially keep finding more and more data. Okay, so now I'm going to turn to, that's a property prediction. Let's turn to the potential energy surface. And I want to be able to do the potential energy surface because I'm interested in chemical reactivity. All right, and so there was a kind of a, so what, you know, what are we trying to do? So we're going to develop a new architecture. So as I told you already, which is that, you know, machine learning models are kind of dumb as doornails. Okay, I don't know anything, you know, so you have to teach them everything. Okay, and so the main point here, as I said, you got to teach them those symmetry operations. And if you don't teach them the symmetry operations, they won't predict correctly. So there was this effort that we created to develop, and so a lot of machine learning models back in 2020 when we were working on this are so-called invariant models, and they require a lot of data. And the benefit of doing something like an equivariant machine learning model is to build those symmetry operations directly into the architecture. Don't try to do it through the data. And if you don't do it, and if you do it that way through the architecture, you're going to require less data. And remember, data is precious and it's expensive to generate. All right, and so what we developed then was this method called Newton net. And it's a message passing neural network, and effectively then the features, okay, of the network are the forces, but furthermore, the forces have to satisfy a symmetry operation, which is that it's Newton's third law, which is that the force is equal and opposite, okay, between a pair of atoms. And if you build that into the network, then it turns out that it enforces equivariance. So that means that if I wanted to apply that to, you know, to chemical shift prediction, I wouldn't have to do data augmentation anymore. I would just simply now, you know, preserving that through the network allows me to make predictions without having to do the extra data. All right, so let's see this data reduction and let's see accuracy first. All right, so this is these are some of these famous data sets. This is, you know, where someone has been able to develop CCSD parenthesis T and the complete basis set limit for things like aspirin or benzene, et cetera. Okay, and so, and then there are available energies and forces, okay, on this data set. And so this was another, like I said, it was a kind of an arms race at the time. A bunch of us were developing equivariant models all at the same time. And this is a well-known one from Tess Schmidt's group called NEquip. And this is sort of a rank 1 method. You can effectively doing spherical harmonics. And so you can go to higher order spherical harmonics in this model, and things can get more accurate. They also get more expensive. And so Newton net is kind of a rank 1 model. And what we can see is that we can make, you know, this is in errors on the order of kcals per mole. Okay, so we can get energies and forces predicted really well. So that's the accuracy that we can get. And then here's the ANI data set. The original ANI network was sort of getting energy errors that were about 1.3, so like 2 KT errors, you know, that's pretty large, and so kind of not acceptable. And this is just showing that Newton net with 1/10 of the data, you know, 10% of the data is well beating that energy prediction, and you can go to 5% of the data and still beat it. And so the idea here is that this is the evidence that equivariant models just require less data, okay? And then methane combustion, this was a bit messy. This was published by someone else, but we decided to develop our own network, and we decided, our own data set. So this is hydrogen combustion. And I thought hydrogen combustion was going to be so simple, right? It would be hydrogen and oxygen, and it would be the world's easiest thing to do. And of course, it was the world's hardest thing to do in the end, because there's tons of spin states and all kinds of, and the fact that, gas phase, right, which is that, the reactive space, overall, the potential energy surface is enormous, okay? Unlike a homogeneous liquid like water, which is actually really easy to predict by machine learning. All right, well, anyways, naively we set off. And here what I'm showing is, we can get down to good chemical accuracy, okay, with a fairly small training set of energies and forces of our Newton method compared to, which is in green down here, sorry, compared to these invariant models, okay? So they kind of top out, and we can beat those, which is great, okay. But here's what I wanted to do. At the time, everybody was really, like I said, it was an arms race where everyone was just trying to say, well, I can squeeze out another 1/10 of a kcal, so therefore, I didn't want to do accuracy anymore. I think these are already accurate enough. And what I wanted to do is to say, well, can we do some chemistry with these? Which is, I've learned some potential energy surface. Why can I do something predictive now? I want to predict something the way you would do a physical model. All right. And so here's this hydrogen combustion. And here's, for example, is a intrinsic reaction coordinate for one of the roughly 15 to 20 reaction channels, okay? And so that's what involves, I can't see it very well, one of the reaction channels. And so this is all the data that we collected. We had a lot of reactant and product states. We did AIMD off of the IRC transition state. We did systematic normal mode calculations along the IRC to collect data. So we collected a lot of data, and it was a pretty good functional, pretty decent basis set. So that therefore, we're trying to do something predictive in hydrogen combustion. And so the question that I wanted to ask was, is there any entropic component to the transition state? In other words, is the IRC at 0 Kelvin all I need to know? Or if I go to finite temperature, does the transition state move on the free energy surface? And so what you can do is committer analysis. I can start here at finite temperature, and I run reactants and products. I sort of just ask, do I fall into the reactant or the product? And what we can see that for a lot of the reactions, like reaction 3, yeah, that seems to, mainly enthalpically dominated. Okay, so that means that that's a pretty good transition state. But for reaction 1, like I'm showing here, well, somehow that's actually not the transition state at finite temperature. All right, so let's try to do something. Okay, so Nancy did a great job on this. We start trying to look for it. Okay, so we start looking for these transition states. All right, what I'm showing here is that, so we naively start off. And like I said, when you think about a physics model, you never have to say molecules are more stable than atoms. Okay, we should probably know that. But it turns out that, of course, a machine learning model doesn't know anything of the sort. And we forgot to put in atomization energies. And if you don't have atomization energies, then the very first thing that happens when you start running on the machine learned potential energy surface, you're running, F equals ma, where F is coming from the machine learned forces, then you start atomizing. And so we're like, oh, shoot, okay, sorry, that's my bad. Go get those atomization energies, put them into the model, retrain the model, which is sort of a workflow and days of work to try to kind of do that thing. And we fixed up that problem, okay? All right. And then what happens is that, and then once you've done that, you can sort of, let's say you're running in the NVE ensemble, you should get energy conservation. And what you can see is that I found that problem. And then, sometimes you would run into these problems where you get energy discontinuities. It's like holes in the potential energy surface. And so the forces will go kind of crazy. So then you sort of find that data, you retrain, And then you get back to doing the science problem that you were trying to solve. Okay, you get energy conservation again. And so actually, that's the potential, and this is the total energy here. So things are looking good. Okay, great. All right, so we continue. And here we're running reaction 16. And it turns out that the iris, this is one of those cases where we think there's an entropic component. Okay, so we're trying to find the transition state. And then all of a sudden we get a hydronium. Well, because it's never seen a hydronium before. And it turns out that the machine learning model thinks this is a very stable species, but you go back to the data source and you actually find that it's a high energy species. So what I'm trying to kind of emphasize here is the fact that how am I going to ever discover anything? You know what I mean? If I have to just keep going back to the ab initio source, it seems kind of circular logic to me, right? Which is that, anyway, so the thing is that, we're wrestling with this. And so like I said, we keep running into these holes into the potential energy surface. And so the way you discover this is, again, like those committee of machine learning models, which is that, you keep sort of, you're running 4 of these models at the same time, all started with different initial conditions. And therefore, when you hit a hole in the potential energy surface, they show large variance. And so then this is just showing that they can just go kind of crazy. Their trajectories look really kind of crazy, and they just start kind of accumulating in the corners of the collective variable space. All right. And so the thing is that what I wanted to kind of then say is that I think one of the things that's wrong in chemistry of machine learning is that we all think like chemists, and we all think about the fact that, okay, there's reactants, there's products, there's metastable states like transition states, but we don't think about the fact that there are just lots of unphysical regions of the potential energy surface that will never be visited. But if you don't tell it, the machine learning model, about those regions, it will go there, and it shouldn't. And so the idea here is that we need negative design principles in our data. We need to think about how to generate data that is not the way we think about a physical model. Okay, a physical model has got built into it that you won't visit certain regions. Machine learning's got to be taught that. Okay, all right, so therefore, what we propose is that metadynamics, turns out that Michele Paranello's group and our group came up with the same idea, which is that let's use metadynamics as a way, it doesn't matter how good the collective coordinates are. So this is a way to essentially rapidly explore configuration space in a lower manifold. Okay, so you pick 2 coordinates that you think are going to trap the region of interest, and then you're going to sample in that. And so therefore, but when you look at those regions, you can get really high energy states in those regions. And the main point is that we can use metadynamics as a way to rapidly get, okay, these unphysical regions, okay, to be able to train our models, okay, because they're really meant for rare events. Their idea is that they visit high energy states. So let's use that, okay? So this is the combustion data set. We train the N4 models, we run through metadynamics, and then that variance among the models tells us that, well, we got a problem. We got to send that back. We got to then do all this DFT calculation. We retrain the model and we start again, okay? So I think the thing that I really want to emphasize is how much work that is, okay? I mean, I might as well just do an ab initio calculation. I was beginning to think at the time, I was getting frustrated. I was thinking, why don't we just do the ab initio calculations? But anyways, all right, so Nancy then says, no, we're not going to do that. And so we're going to, let's try to systematically sample in what she calls the dilation data set, which is just to simply systematically sample these high energy states and add them back in. And that's where metadynamics is pretty good about having us visit these unphysical high energy states and species. Okay, and it's good for ergodicity as well, because we're in this lower manifold. All right. All right, so that's what we did. And then so now things are better. Things are a lot better. And it turns out that I can now run 1 million steps of ab initio quality dynamics, okay? Quite easily now with the machine learned potential. but a fraction of the time, I will fall into a hole. And this is what I think about the potential energy surface. Any potential energy surface of interest is going to be so high dimensional. I just can't see how we're ever going to cover it in a machine learned model. And so therefore, let's come up with a hybrid model. Let's essentially say, at some point, I've learned the potential energy surface well enough so that 99.5% of the time, I can run an ML step that is accurate. And then 0.5% of the time, it will be a lot cheaper just to go out to the original data call and just go get those 1,300 times where I have to just do the DFT calculation. And that's cheaper. That's cheaper than essentially having to keep retraining and retraining and retraining the model, okay? And so that fills in the holes of the potential energy surface. And so finally, we get some chemistry out, which is that reaction one, okay, actually wasn't as bad as we thought, but still, okay, there's a free energy transition state that's moved, okay, due to the entropic component. A lot of these things were problems with the potential energy surface. In other words, we're seeing lots and lots of examples of where the intrinsic reaction and transition state is now pretty much giving us 50-50 statistics. But there's about 4 reactions which have a difference. And so we finally can perform some chemistry. And so what I'm showing here is that out of the 4 reactions, here's 2 examples. One here, this was the original transition state of the IRC. And what I'm showing here is that the new transition state in the metadynamics is actually a bifurcated one. Okay, so we get 2 saddle points. And now if I do committer analysis off of those points, I actually end up in the reactant and product basins with the equal probability. So there was the real transition state in the full dimensional space. And the same thing here is another dramatic example. This is for reaction 1, which we've been illustrating throughout this section of the talk. This was the original transition state. You can see that it's very, very, the IRC one, this is just very, very different because it has a free energy and therefore entropy component that brings it way over here, okay? So you're learning the differences about, now to me, I think we finally made a prediction, okay? Something that we wouldn't necessarily be able to do as easily with ab initio molecular dynamics. Okay, and I just wanted to say, we talked about this at dinner last night, but I kind of wanted to show this data, which is that, you know, these aren't necessarily optimized machine learning models, but they give you the sense that if I was to try to do all of this in QChem, that it cost me about 12 seconds per time step to drive the MD, okay? Whereas in the machine learning, you get about 2 orders of magnitude, especially if you do it on a GPU. So that's where you're going to, so, you know, the idea here is that ab initio molecular dynamics has got a competitor in speed, but I will argue will not have a real competitor. It will be a complementary technique with machine learning. And I don't think that you would ever get these to essentially replace the force field, because force field time steps, like the cheapest force field, are something like 10 to the minus 7 seconds per time step for a gigantic protein and water system. Those have been super heavily optimized. All right, we can do more optimization here, but that's the promise of machine learning, is 2 to 3 orders of magnitude in sampling, okay, which you couldn't do. All right, so then I was going to turn to this the other thing that we get out of this is that if we have now a fairly well-trained hybrid model, but let's say just a trained potential energy surface on this data, let's apply it to some new data, okay? So what we're going to do then is we're going to say, what if I now try to get Hessians? Okay, I'm not going to do MD anymore. I'm not going to just get forces. I'm going to now, you know, try to go find transition states, and Hessians are very helpful for doing that. And so the thing is that you know, what you'd like to do is what's called a Newton step. You would like to be able to calculate a Hessian at every time step or every step in your transition state search. But that scales as order n to the 4th in an ab initio case. And so therefore, that's just not tractable. So what do you do? Which is that, well, there's been a lot of research in transition state finding, which is trying to come up with a good initial guess, okay? And then the other thing is that, you know, or you can develop these quasi-Newton methods, which you're constructing approximate Hessians through gradient information. But that's only approximate, and the error ends up accumulating over time, okay, with that. Okay, so like I said, which is that these are the things that are, all these things are what is the current active organic chemist toolbox, is to essentially use quasi-Newton techniques, but only on the initial start to a transition state search, with essentially all of these heuristics that are helping you find a transition state. All right. So the question that we wanted to ask is whether we could come up with transition state searches where we could actually just drive it by the Hessian and therefore just do better at trying to find transition states. So that's our Newton net model again. And the only thing that's different is that we don't stop here. We auto-differentiate it with respect, one more time, we auto-differentiate the network to be able to create the Hessian. But we don't use Hessian data, okay, which is that this is just based on energy and force training. And what we're hoping is that that is sufficient to be able to predict Hessians, okay, by now just auto-differentiating one more time, okay, but without Hessian training, okay. All right, so fortunate for us, there was this transition 1X data set, okay. So remember I told you about the Annie data set. And so now what we have are a group that developed, you know, took the organic, which are really combustion, well, what they are combustion reactions, really. They took the anti-organic data set and they essentially then proposed, you know, with nudge elastic band, generated a lot of transition states. So they have about 10 million data points, about 10,000 different gas phase organic combustion reactions, all evaluated with a pretty lousy level of DFT. So you can't really do anything predictive with it. All right. But like I said, but this is the machine learning model fully differentiable. And so with that energy and force data, we're going to then predict Hessians. And then what we did is we worked with Judith Zador's group to interface our machine learned Hessians with this open source software package called Cella. And Cella is a really good state-of-the-art transition state finder. It uses quasi-Newton, it uses geodesic type of searches. It's a very, very, very sophisticated, but it works on physical models. So it's never been interfaced with machine learning before, okay? And furthermore, everything was quasi-Newton because you couldn't afford, you know, no one really does full Hessians. So that all that had to be adapted, okay? All right, so now we have some ways to do. And so this is what I wanted to show you, is that effectively to look for a transition state, it takes us far fewer numbers of steps to do that now. 2 to 3, 50%, you know, 75% reduction in the number of steps to get to the transition state when I have full Hessian information. And the harder the transition state, the fewer steps I have to take. So things kind of flatten out over here, even though the quasi-Newton DFT calculation has to, you know, has to take a lot of steps to find the transition state. And the second thing is that we can see that the full Hessian is more confident, okay, in the steps that it takes. It can take larger steps, okay, and following a quasi-Newton, and because we're not using a quasi-Newton approximation, we're using a true Newton step. All right, and then just simply saying that the path length that we're getting, we're staying on the path, okay? It's a little bit hard to see, but what I'm trying to show here is this orange curve is saying that the path length, we don't get distracted, okay, and get off path the way you do with a little bit more with the quasi-Newton, okay? All right, so that's the benefit of cheap Hessians, okay? And then what about robustness? So what we have is a test set of 240 reactions, organic chemistry reactions, never been seen before. All right, and so what we can see is that that what we call two-sided, what we're referring to is that Cella has this sophisticated thing, which is that if I have a reactant and product, it will have a transition state guess that will be consistent with that two-sidedness, okay? All right, so that's called Kinbot. Anyways, and so the idea here is that this is the DFT, this is the quasi-Newton machine learned, and this is our full Hessian machine learn. And what we do is we just do systematically better. And for reasons that we cannot understand, we've been unable to uncover, the machine learned quasi-Newton does better than DFT. Okay, I don't know why. We've tried so hard to try to understand that, but cannot really, we don't understand it. It just doesn't seem to, maybe it's the 240 reactions. This would even out if we had more data. This is actually showing that if I added noise to the initial guess, what if I had a poor initial guess? Well, DFT, you know, that it essentially starts failing, okay? Whereas if I have the Hessian can recover from a better with a bad initial guess. And that's what this data is showing. So we're implementing that with just noisy inputs. And then you might say, well, okay, you found transition states. Are they real transition states on the DFT surface? And this is showing that we get 95% of them are negative eigenvalues on the DFT surface. And so that's right. And we got some of these outliers, in particular, these ones have positive eigenvalues. But remember, we're on the machine, this is with the machine learned structures. And the point is that's not necessarily the stationary point on the DFT. So if we re-optimize them, then essentially they fall over into transition states. So there's just a bit of a perturbation that essentially drives these back over here. And we can see that over here, which is that we get increases. And like I said, then one end matches is just referring to the fact that we just get a different product. In fact, we find more stable products. And that's why we only have a one end match, is that the prediction of the product is actually, we find a better one. We find a better transition state, if you sort of see it from that point of view. And given the fact that we're doing organic reactions, some of those reactions might find conformational transition states. They're not real reactive transition states. And again, we do a lot better, okay, in regards to finding real chemical transition states. And that helps get cleaned up, okay, after we optimize with, the way to think about this is that the machine learn can provide a good initial guess to a DFT calculation, okay. All right, I think I'm going to very, 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 very quickly, because I just want to show Ufan's work because she's here. She was from Cornell, but I'm going to make this really short. This is the IDP area. My long-term collaborator is Julie Foreman-Kay, who's an experimentalist. And so we've been doing machine learning, okay? And why do we want to do machine learning? Well, these intrinsically disordered proteins are not like folded states. They have conformational heterogeneity. And it turns out that therefore they have a lot of function. Okay, in other words, they have a lot of plasticity that apparently is really important. We're made up of a lot of IDPs. And so this is all the kind of functions that they can do. They do these interesting things called liquid-liquid phase separation. But anyways, the problem is that it's not like we can do X-ray crystallography with them. And therefore we have to rely on solution experiments, and those become highly averaged. So we can't tell. It's like it's an underdetermined problem. And so you need computation to do something. And that's what we did here, is we did some machine learning about being able to make predictions of conformational ensembles that are in agreement, at least with the solution average data. Okay, and I'm going to skip this and just simply kind of show you that this is a degenerative recurrent neural network that we developed, where we just literally grow the protein, okay? We grow the protein torsion by torsion, okay? Backbone by, backbone torsion, side chain torsion, depending on the sequence. And that this is a type of network that's able to essentially grow these IDP chains. And then what we're going to do is we're going to do what we call reinforcement learning to get it to agree with the data. Okay, so the idea is that Julie gives me chemical shift data, she gives me J coupling data, doesn't matter. I'm now going to bias the distribution, okay, of these generated configurations so that they end up essentially as an ensemble average reproduce the experiment. And this is how it works. And this is just showing you that with J coupling data, we get this new, you can see that the nature of the underlying populations, this is the phi value, okay, of the IDP ensemble, carves out, essentially says, nope, there shouldn't be so much population there because the experimental data is driving the ensemble to new states, okay? All right, and then I'll just say we applied it to histatin 5 and alpha-synuclein, and we get really, really nice agreement with experimental data. All right, so I'm going to conclude. I'm going to say that chemical shifts are very difficult theoretically, and I think that machine learning really is performing, can reproduce that ab initio theory, that expensive ab initio theory pretty well. Active learning is working pretty well. I do think that trying to get this to work for aqueous systems of proteins really hard, which is that we need to model all the vibrations and conformations. I think we can calculate the ab initio, but it's just all of the sampling that's the current difficulty. And then, like I said, I think that this hybrid model and the ability to exploit the potential energy surface through second derivatives offers a lot of interest and hope, okay, that we can actually really drive new chemistry with machine learning and physics. And then I only briefly introduced this to you other than say that this is starting to kind of replace some of the traditional Bayesian methods. All right, so I'll stop there by thanking all of the great people. I think I've done an adequate job of introducing them at appropriate stages of the talk, and to also thank funding sources. And I'd like to thank you very much for your attention and for hosting me for such a fun 2 days. So thank you again.
Any questions? Rob?
Yeah, so one question I had was, I think going back to, I think it was like the third slide or so, where we were talking about how without the exchange, right, calculational, without hybrid functional, right, we can't predict chemical shifts. Is there a physical reason, like in terms of the calculated energies, why non-hybrid can't account for that?
Yeah, just because the whole premise of DFT is that it's based on the electron density, but there's no underlying ansatz that it should be able to do anything without magnetic properties. Yeah. Yeah.
Rob?
Thanks for fascinating. We had a colleague, Barry Carter, very interested in the deviations from the normal IRC controls that we have. Now, one way to characterize those are the ones that do not get 50-50 from the emitter, is that there is a flat region on the potential. Is that what your second derivative work helps us identify quickly? How can we identify things which have a large entropy of activation, which is what we call?
Yeah. So I think that I was working in this idea of this entropy flattening, I guess is the way to think about it, through the kind of the usual physical model of metadynamics. If you can find the right collective coordinate to trap the transition state, you'll find it, okay? And so the point is that we've done that with the machine learned potential. But now what we then did is to sort of so then we worked on these Hessians. And so the idea is that I guess they could be combined. But what I will say is that if the Hessian is going to report some different type of curvature, it's all there. And so the point is that we could just analyze the Hessian of the IRC if we wanted to. And then I guess what I'm saying is that, yeah, so then the Hessian, if that is a way that would contain that type of information, I think it should be evident, right, in the Hessian, just based on it being a property of curvature. But we haven't put the two together yet. Yeah.
Looking for something to tell organic chemistry when a suggested reaction mechanism is going to be not simple hierarchy. It's going to have a large entity.
Right. Yeah. All I can do is to say is that I've already tried to talk to John Hartwig at Berkeley about this. And you're right. He just wants to, what they do is essentially try to find descriptors. So that's a descriptor, is how flat is that region. And the point is that they've been doing kind of machine learning, but using descriptors to essentially try to chase down transition states, right? And so we have a different descriptor, which is the Hessian. And I'm saying that, and so I've been talking to him about whether we might be able to collaborate. Well, when I showed him these reactions to show you how much of a physical chemist I am, I didn't realize that these were combustion reactions. I just thought there's organic chemistry stuff, you know? And so it turned out that he was looking at these reactions. He goes, but this will be impossible. Like, you can't do this. Like, that's what you only would run at 500 Kelvin. And I said, oh, and that's when I knew that actually our data set was a combustion data set. So we would have to work with John, and he's interested in transition metals. And so we would have to go generate, again, new data. Because he's interested in transition metals, I don't think that learned surface is good enough for that. But if someone had some room temperature organic chemistry, I think these models would work. But anyways, I'm just trying to say that I know what the organic chemists want, and they want something cheap and fast and now. And I don't have cheap and fast and now right now. Okay.
Wow.
The hybrid approach of statistical and AMD, how do we know ahead of time, for certain configuration we are not confident about the movement potential and we have to do AMD? What threshold can we use to apply for constant score that is below that threshold that we have?
Well, I think maybe what you're asking is that when do I stop training? Is that what you're asking? Because what I'm trying to say is that you're going to get 2 orders of magnitude that you're not going to get with AIMD. So if you want to exploit that, then you're going to have to train. And I'm trying to argue that you got to think about your data. What data do I get? You got to teach it dumb stuff. You got to teach it high energy stuff. Okay, so now you're finished. Okay, then at some point, I think there's a frequency that is where I want 2 orders of magnitude. So I'm not going to essentially accept 50% failures. But once I get up to about 20%, 10%, 5% failures of the machine learned model, then I'm still going to get 2 orders of magnitude, but I'm going to fill in the holes with the original data source because it's a drop in the bucket every once in a while.
Like 90%, right? We don't know ahead of time.
No, not right now. I mean, this is like, I think machine learning and chemical reactivity is still in its infancy, meaning that maybe eventually we'll start figuring out stuff like Roald is saying, we'll figure out how to recognize, how to train better or how to avoid holes in the potential energy surface. I don't know. I guess I'm just saying is that, no, there isn't a magical predictor except the fact that we've got a committee of machine learning models telling us that apparently they don't know something. Okay.
I have a really general question. So for these machine learning approaches, and say you have a model and it's not as effective as you would like, how do you know that it's the data, like it's not trained well enough, it doesn't have the right data, or it's the architecture or the encoding, or what I mean, the actual model itself? How do you distinguish that?
Well, there's something called the variance bias trade-off. Okay, and that's one thing is that you can have a holdout data set. And what you do is you're running your training and you're asking how is it performing on the validation set. And if it actually starts if it reaches some level of accuracy that you're just completely unhappy with, like like you're making 5 kcal per mole errors, then there's something wrong with your machine learning model. Okay, so you got to fix it then at that point. The other case is what's called high variance, and that's because the training just keeps going down, but the variance starts going up. And that means you have too much data. And you need sort of to now to maybe do some feature engineering in order to get data requirements down, or transforming the data in some way. So those are the sort of early ways to kind of figure that out. And then, like I said, then there's lots of different architectures. And so you got to think about your problem. That was the right architecture to use. Does that answer your question sufficiently? Yeah, okay.
Well, you talked about building in the physics of the problem. Have you built in computational chemistry?
So in the second part of my talk, there's 2 ways to build it in through the data. And that's where you just simply, yep, okay. And then the other way is to do what we did with NewtonNet. You build it into the architecture. You're trying to essentially explain symmetry operations, or you're trying to embed symmetry operations into how the architecture performs. And that's the second way. Okay. And that's what we did with NewtonNet. So that's an equivariant model. Requires much less data because it doesn't need to learn those symmetry operations. It's already in the network.
So I have a question about the equivariant network. So when you say equivariant, does this mean like when you figure more equivalent? I know we were both predicting the ambient force because the energy is invariant and the force is always equivariant.
So the forces, that's right. So the energy shouldn't vary, but the force, but the force vectors, have symmetry operations that, internal forces should be the same, right? And so how to predict what? Oh, the Hessian. That one, we didn't use Hessian data. We just, because it's learned energies, and you take the second derivative of the energy with respect to particle position, which is how well, let's start over. Take the derivative of energy with respect to particle position, you get forces. You've learned that. And so now what you're doing is the weights of the network have adjusted to learn that relationship. And now what we're doing is just auto-differentiating the network to take the derivative of the output with respect to the weights is equivalent to the output of the energy, the second derivative of the energy with respect to the positions. Is that clear? Yeah.
Yeah, so it was a really interesting idea of running the force field going back to the input. It reminds me most of when we go run a GROMAT calculation and you look down the log file, every now you'll find these lines where it hit a point where the potential blew up and then said, okay, this is really bad and then restart it. And there it's almost as if you're doing that, but instead of restarting, you're actually calling back if you have a score. If you can go further back. And I guess my question is, in the future, do you think that, now that the machine learning people, we're a little grubbier, we don't care that much about accuracy, that maybe people want the background. Do you think that just simply restarting with the accuracy would solve that problem?
I don't know. I think that the variance among the machine learning models is saying that if you were to restart there, you would just, well, I mean, well, no, but then at that point you're off into a different trajectory. So we already know that you'll get shadow trajectories that won't hit that point again. It'll hit some other point at some point. Yeah. 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 So, yeah, I mean, anyways, we came up with the solution that let's go back to the data source because we want to continue trying to drive things forward. And so that's what we decided to do. Okay, yeah.
Any other questions? All right, if not, let's thank Teresa again.
Thank you, guys.